Every Python developer hits the same wall on day 3. I want to show it to you now. You have probably been taught that a variable is like a box, right? You put a value in it, and that box holds it. That mental model works in many languages, but in Python, it is fundamentally flawed. If you stick with that box idea, you're going to run into some truly baffling bugs, especially when you start passing things around in functions or dealing with mutable objects. I know, because I spent 3 days debugging something that boiled down to this exact misunderstanding when I was starting out. Today, I am going to show you why that box analogy is dangerous and what the correct mental model is. This isn't just academic. Understanding this mechanism is critical for writing correct, predictable Python code. It impacts everything from how you manage memory to how you debug unexpected side effects. We are going to rip apart that old idea and replace it with something that actually reflects what Python is doing under the hood. By the end of this, you will understand how Python variables are actually references to objects, not containers. You will see dynamic typing in action, reassigning different types to the same variable name without a fuss. We will use Python's built-in ID function and type function to peek behind the curtain, inspecting an object's unique identity in its runtime type. And finally, you will be able to identify those common type error scenarios that pop up when you forget what type of object you are actually working with. So, let's ditch the box and think of a Python variable as a sticky note. When you write something like x equals 42, Python does not put the number 42 into a box labeled x. Instead, it first creates an actual integer object with the value 42 somewhere in memory. Then, it creates a sticky note, labels it x, and writes down the memory address of that 42 object on the sticky note. The variable x is just that label, that reference, that pointer to the object. It is not the object itself. This is a fundamental difference from languages like C++. In C++, when you declare int x equals 42, the variable x itself is a specific memory location on the stack, sized to hold an integer, and the value 42 is directly stored there. In Python, x is a generic reference, typically an 8-byte pointer on a 64-bit system that can point to any object anywhere in memory. The actual integer object 42 lives on the heap, managed by Python's memory allocator. The variable x just holds its address. When I first saw this, I thought, okay, so what? But this distinction is everything. It means that multiple variables can point to the exact same object. It means that when you pass a variable to a function, you are passing a copy of that sticky note, not a copy of the entire object. And it means that the type is not attached to the variable name itself, but to the object it references. This is the core of Python's dynamic typing. To prove this, Python gives us two powerful built-in functions, ID function and type function. The ID function returns a unique integer identifier for an object, which is effectively its memory address. The type function returns the object's class. Let me show you what I mean. I will write a simple assignment and then inspect it. Here, I am declaring a variable named my_number and assigning it the integer value 42. Then, I am printing the value of my_number, its unique ID, and its type. Notice how I am calling ID function and type function on the variable my_number. But what they are actually returning is information about the object that my_number is currently referencing. When you run this code, you will get output similar to this. You see the value 42. Then you see a large integer, something like 140737351954384. That is the unique ID, the memory address, of the integer object 42. And finally, you see that its type is class int. This confirms that my_number is just a label pointing to an integer object in memory. Now that you understand that variables are just labels, dynamic typing is going to make perfect sense. Python is dynamically typed, meaning you do not declare a variable's type. The type is determined by the object it references at runtime. This is incredibly flexible, but it means you, the developer, need to keep track of what your labels are pointing to. Let's see this in action by reassigning our variable. I will start with my_variable set to the integer 42, just like before. We print its ID and type. Then, on the very next line, I am going to reassign my_variable to the string hello, Python. This is perfectly valid Python. We then print its ID and type again. Notice, there is no type declaration, no casting, nothing. Python just handles it. The output clearly shows what is happening. First, my_variable points to the integer 42 with an ID like 140737351954384 and type int. After reassignment, its value is hello, Python. Its ID is now something completely different, like 140737351954560, and its type is string. The original integer object 42 is still in memory, potentially waiting for garbage collection if nothing else references it. My_variable simply peeled off its old sticky note and stuck it onto a brand new string object. The common mistake here is thinking that the box, named my_variable, somehow changed its contents from an integer to a string. That is not what happened. The variable, my_variable, itself never changed its fundamental nature as a reference. It just changed which object it was referencing. It is like taking a sticky note from one drawer and putting it on a completely different drawer. The sticky note is the same, but what it points to is entirely new. This mechanism is why Python is so flexible. You can write generic functions that operate on whatever object you pass them, as long as that object supports the operations you are trying to perform. But this flexibility comes with a catch. If you are not careful, you can accidentally try to perform an operation on an object that does not support it, leading to a runtime error. This is where TypeErrors come in. This is the part most tutorials skip, but it is where the rubber meets the road. Because Python variables are just references, and the type lives with the object, you can easily run into a type error if you forget what kind of object your variable is currently pointing to. Let me show you a classic example. Here, I am setting data to the integer 42. Then, I am trying to call the built-in len function on data. The len function is designed to return the length of sequences like strings, lists, or tuples. It does not make sense to ask for the length of a single integer. Python will not catch this at compile time because data itself does not have a fixed type. It only knows what data points to when the code actually runs. When you execute this, you get a clear, concise error message. Type error, object of type int has no len function. This is Python telling you, hey, the object you are pointing to with data is an integer, and integers do not have a length attribute or method. It is a runtime error because the type check happens when the operation is attempted, not when the variable is assigned. The fix is to ensure that the variable references an object that actually supports the operation you are trying to perform. If you need the length of something, make sure data points to a sequence type. I will modify the code to show you. Now, data is assigned the string Python. Strings are sequences, and they absolutely have a length. When we call len data this time, Python is happy because the object data references the string Python, knows how to respond to a request for its length. The output is exactly what you would expect, 6. This is the essence of dynamic typing in Python. The variable itself is just a name, a reference. The actual capabilities and behavior come from the object it points to. Always remember to consider the object's type when performing operations, not just the variable name. You now understand 3 critical things about Python variables. First, you know that variables are references, like sticky notes, pointing to objects in memory, not boxes containing values. Second, you have seen dynamic typing in action, where a variable can reference objects of different types throughout its lifetime. And third, you can now use ID function and type function to inspect the identity and runtime type of any object of variable references, giving you powerful debugging tools. Mastering this concept is going to save you countless hours of debugging. Next time, we get our hands dirty with the actual building blocks of every program, fundamental data types, numbers, booleans, and none. I will see you there.